So we're kind of winding down chapter 10. And so we have 10.6 that we're going to work on today and tomorrow and Thursday. That way you have, 2 days of it. So we definitely have time to go over any of the implicit differentiation if we need to. The good news about this last section is it's called related rates. And so we actually find values, which makes it a lot easier to understand what you're doing. That implicit differentiation, what we did last week, it's very abstract. And what I mean by that is you have a lot of variables that you don't know what they are. And so you're kind of just trying to manipulate the equation or the function or non-function so that you can come up with the right implicit differentiation. And so sometimes it gets a little bit wonky in the respect of I don't really know why I'm doing this, but I know my algebra and I have to do certain steps to get the algebra right. And so you just kind of have to trust the algebra that it's gonna bring you to the right answer. So what we're going to do today is we're going to kind of apply the same concepts, the same tools, but we're going to apply it in a very real setting. So I'm going to start with, so this is something from my childhood, my teen years, if you will. And it's been something, and you'll understand why it's stuck with me all these years. But it's how things happen in your life and you go, oh wow, you'll never forget that moment, or the lesson learned sticks with you forever. And so that's one of these experiences that I had as a teenager, and it has stuck with me forever. So when I was in high school, 16 years old, I was in my sophomore year, junior, I think it was my sophomore year. And I was 16 years old. My dad was 46. He and I were very, very close to each other. I used to go work with him all the time. He was a golf course superintendent, so I got to drive the golf carts around. And he had a brain aneurysm and died. And so it kind of put me on a track of, because my mom was a stay-at-home mom. She got her cosmetology license, but she never really worked. She was always home. And she did, odd jobs and stuff, but she never was like working outside the home. There were 5 of us kids. And so I'm number 4. So I have an older brother, sister, brother, me, and then a younger brother. So there were 3 boys and 2 girls. And so, obviously it devastated the family. He was the main income generator. And so I watched my mom have to go to work, and she ended up in a laundromat folding other people's clothes. And so it kind of put me on a trajectory of, I'm not going to rely on someone else. I'm going to make sure that if anything happened, I could take care of myself and I would have a career. And so I was the first one that went to college in my family and finished. My older sister took some classes, she never finished. So that was November. And so now we're coming into the holidays. So it was right before Thanksgiving. It was early November, right before Thanksgiving, that my dad died. And so now we're coming into December. And for the 2 weeks before Christmas break, I'd go into class and there would be an empty seat. And so it started to become this pattern where every day I'd come to class and there'd be an empty seat. Well, what was happening was there were several car accidents. A couple of them were, drunk driver. Somebody got hit by a drunk driver. There was one suicide, which was very, very sad. But there were several where the car was full. And so like one of them, it was a drunk driver. He blew through a red light and T-boned a car, and the car literally exploded. It was, it doesn't happen very often, but it can happen. It just hit just right where it exploded. And so there were 5 students in the car and they all died. It was horrible. And then another time, a car was, a student was driving and he was doing doing this down the road. So the car was going back and forth. Well, the car flipped and 4 people got ejected because they weren't wearing seatbelts. And the only one who survived was the driver. So that was 4 more people. And then another one, and this is the one that I that has always haunted me, is there were 5 people in a car again, and another, again, they were all students. And we lived in the Palm Desert, Palm Springs area, Southern California, so it's very flat. And so there was a car next to train tracks. And so this car was racing the train, and they decided they were going to try to cut it off. So they were racing the train, and then the guy, they were coming to an intersection, and the guy driving the car tried to cross the train tracks. The train hit it, and of course, everybody in the car died. And so within those 2 weeks, there was about 20 to 25 students. I don't remember exactly because it was many, many years ago, but it was between 20 and 25 students that had died just from my school. And so obviously those kind of things are going to stick with you. Well, when I started teaching this business calculus, within 2 weeks, Gabe, it was crazy. And then, 2 weeks prior, my dad had died. So there was a lot going on. But this problem that came up in this business calculus class has just stuck with me. It has just stuck with me. So I'm going to share my screen, and I don't want you to take notes on this, just because I want you to really watch what I'm doing. So what we're getting into is what's called related rates. And so because we're talking about, did I share my screen? Hang on, sorry. Thought I shared it. Here we go. So because we're talking about derivatives and implicit differentiation, we're going to have different variables, right? And what we're looking at is how are things changing? So when you guys drive to school or are in a car, your speed is the rate of change from your miles to hours. So you're changing the number of miles per hour, right? It's a derivative. That's what you're doing. You're finding out how much is your car changing in position based on hours. Okay, so here's your scenario. So you have a train and a car, and you're coming into this intersection, and the first thing I want you to notice is you have a right triangle. Okay, this is a right triangle. So here is my right angle. Here is one leg, here is the other leg, and here is the green is the hypotenuse. Okay, so what formula comes to mind when you think about a right triangle?
Pythagorean theorem?
Yeah, the Pythagorean theorem, which is a squared plus b squared equals c squared. Okay, so if I use these variables, this could be a and b, and this could be c. I'm going to use and change the variables to match what I have here. And variables don't matter. What I use doesn't really matter. It's just an unknown. So I'm going to change this and this to x and y. Okay, so we have x squared plus y squared equals c squared. We'll leave the c alone. Okay, now the car is 0.6 miles away, so 0.6 of a mile away from the intersection, and it's going 80 miles an hour. Well, this 80 miles an hour is actually, we're decreasing our rate. okay? It's going to be a decreasing rate. So we're going to use this as dx dt is -80. Okay, so notice now I'm finding how my car is changing, how this distance x is changing based on time. Okay, based on time. And then my distance, or the x, is 0.6. Okay, over here, the train is 0.8 of a mile, so it's further back, right? It's further away, but it's only going 60 miles an hour. So my derivative, the change in y over time, is going to be -60. And again, it's starting to slow down. So that's that change. The change is slowing down. Okay, and then the distance again is 0.8. So if you look at this scenario, we can kind of figure how fast is this distance closing. Okay, how fast is that closing down? My car is going 80 miles an hour. My train is going 60 miles an hour. How fast is that c distance closing down to where these two vehicles are gonna meet? Okay, so what would you guess? Put a guess in the chat. How fast do you think that c distance is closing down? Just any guess based on the car going 80 and the train going 60. Do you think it's more? Do you think it's less? What do you think? Go ahead and write it in the chat for me, what you think. Just give a guess. Okay. So Nathaniel, you asked how would we describe it? So what I'm looking for is how fast is this C closing down? Oh, in miles per hour. Yes, in miles per hour. How fast do you think it's closing down in miles per hour? Okay, we got a -20, a -40. So 20 miles an hour. Okay, all right, all right. Okay, so let's figure this out. So, everybody at 16 to, usually around 25, they start getting a clue, believe that they are going to live forever, right? I'm invincible. Nothing's ever going to happen. I can tell you quite honestly, driving down from Kerrville 3 times a week to San Antonio, the worst drivers are right there by UTSA. And so I'm going to completely generalize and go, there's a lot of young drivers driving around UTSA. And that's where all the close calls, if I've had any close calls, it would be right there with someone speeding, weaving in and out. It drives me nuts. It's like, just calm down. So the idea that I'm young and, I'm invincible and I'm always going to be around, that is kind of a mindset that is very prevalent in, as soon as you get your license, you feel like, nothing can stop me. So what happens is if I'm going 80 miles an hour, I'm thinking, oh, and the train's only going 60, no problem. I can beat this train. So what we're going to do is we're going to use implicit differentiation to find out how fast is this distance going. Okay, so I set this up kind of nicely. And what I'm going to do first is I'm going to find this distance C. We know the X is 0.6. We know the Y is 0.8. Now let's find out how much C is. What is that distance? How far away, from these two sides are we at this point? So we're going to plug in our 0.6. We're going to plug in our 0.8. And we're going to find C. So 0.6, and I did this on purpose to make it kind of flow nicely. So 0.6 squared is 0.36. 0.8 squared is 0.64. 0.36 plus 0.64 is a solid 1. And then to get C by itself, I'm just going to square root both sides. So that C value is 1. So this is 1 mile, which, you know, if you looked at a mile, it's 5,280 feet. It's pretty far. It's pretty far. So I would look at that scenario and go, oh, I'm going faster than the train. I have a mile before, you know, that distance is going to close down. I should be good to go. Okay. So the way we're going to do these related rates is we're going to ask ourselves 3 questions. Okay. Here's the first question. And I'm going to go over this again. You'll see this again. The first question is, what are we finding? So in this case, we want to find out how fast, this over here, how fast is C changing over time, right? So what we're looking for is, how is C changing over time? We're looking for dc dt, the derivative or the change of C based on time. Okay, that's what we're looking for. Then we're going to write down, what do we know? What are the things that we know? Well, we know C is 1. We know X is 0.6. We know Y is 0.8. We know dx dt is negative 80. And we know dy dt is negative 60. And we know exactly what all these mean. These are all in miles. And these two are in miles per hour, okay, which is a derivative. It's the change in miles per hour. Okay, so this is all the things that we know. And then the third question we always have to ask ourselves, it's, what's the connection? How am I going to connect all of this information to be able to find dc dt? So the connection is going to be our function, whatever the function is. Now, the good news is you guys are going to be given the connection. You're going to be given a function every time. What you're going to have to pull out of the word problems is, what do you know and what do you have to find? So you're going to have to work really hard to get 1 and 2. 3 will be given to you. Okay. All right. So now what we're going to do is we're going to go ahead and use implicit differentiation. Okay. So I'm going to, let me roll this up a little bit. I'm going to find the derivative based on time of x squared plus the derivative based on time of y squared and the derivative based on time of c squared. Okay, just implicit differentiation. That's all I'm doing. And notice now, because I'm basing it on time, my variables are all different, which is where implicit differentiation comes in. Okay, so here we go. The derivative of x squared based on time. So I find the derivative of x squared is 2x. And then I have dx dt, because remember, we peel this 2 off, and then what's left is dx dt. And then same thing here. The derivative of y squared is 2y. I peeled my 2 off. What's left is dy dt. And then the derivative of c squared is 2c. I peeled that 2 off. What's left is dc dt. Okay, so all I'm doing is just implicit differentiation. Nothing has changed. I haven't done anything different than what we learned in 10.5. Okay, what's different is now I have values to plug in. So that's why it's super important to know, what is it that you're finding? Or what is it that you know? What are you given? What is the information? Okay, so I can just start plugging things in. So 2x is 0.6. How x is changing over time is negative 80. 2, my y is 0.8. How my y is changing is negative 60. And then 2, I know c is 1. And look at there. That is what I'm looking for. And if you notice, that's the only variable left. So that's what you want in these. You want to go through, figure out everything that you know, the information that you're given, and with every single one of these, you should have one unknown. And it should be the one that you're finding. Okay, so now we just calculate. So 2 times 0.6 times negative 80 is negative 96. 2 times 0.8 times negative 60 is also negative 96. 2 times 1 is 2, dc dt. So I'm going to add these two. So negative 192 equals 2 dc dt. I want to get my dc dt all by itself, so I'm just going to divide by 2. So my distance of c is changing by 96 miles per hour. 96 miles an hour. Now, some of your guesses were 20, some were 40, but when you're, what's happening, and it's physics, what's happening is because these two vehicles are coming together, this C, this part right here, is moving at 96 miles per hour. It's closing down at 96 miles an hour. So the chances of a car being able to cross in front of a train, even though it's less, or it's less distance away from the intersection, and even though it's going faster than the train, your chances of making it is much less because of that physics of its closing in on itself. Okay, now what this means is this 96 miles per hour, that's what this distance is doing. It's closing at 96 miles an hour. I'm not saying that the car is going 96 or the train is going 96. I'm saying that it's closing at 96. So as it closes and gets almost to zero, those two vehicles are going to come together. Okay, so any questions? And where the related rates comes from is we're comparing rates. So rates is going to be a huge term that you have to remember. Whenever you hear the term rate, what you're looking at is a derivative. So anytime you have a rate or a change, like an increase or decrease, that will always be your derivative. So then when you're looking for what do you know, like what's the information that you're given, you can look for the term rate or the term change, increase, decrease. Then you know you're looking at a derivative. Okay, so obviously that was a very traumatic experience in my life that has stuck with me forever. And I always, you always wonder how can you express to somebody that, one, they're not invincible, not one of us leave this world alive, and two, how can you make good decisions, right? And so that being able to see mathematically that there's no way for that car to pass that train and make it based on derivatives, how things are changing, how fast things are changing. Okay. All right.
I have a question, Ms. Manchester.
Yes. Yeah, go ahead.
This might not have nothing to do with anything, but is the rate closing at the same? Is it equal like on each side, and does that even matter like going forward with this?
Yeah,
Like
I
because
don't
they're going
think.
at two different speeds.
Correct. Yeah, I don't think it doesn't matter one way or the other if it's closing this way or closing this way. The idea is that distance is just closing down at 96 miles an hour. So
Okay.
whether it's, you know, closing faster this way or this way doesn't have any bearing on it. That's a good question though. Yeah. It's crazy though, when you think about it, that it's, you know, 16 miles an hour faster than the fastest car. And that's how it's closing down. So I actually took a class one time from they're called CHPs, California Highway Patrol. And they don't even need to be on site when they're doing an investigation of a car accident. They can do all of the investigation and they can come up with some pretty accurate information, like how fast the cars were going when they collided, how far did the vehicle brake in front of the collision, that kind of thing, just by looking at pictures and just by looking at the damage on the vehicle itself, which I thought was very interesting. But there was so much math that he showed us that they have to do just in the investigation, trajectories. And next week, on Monday, you guys are going to get an announcement. So pay attention to it, and you probably will get it in your student email too. There's something called NVCSI, and it's kind of an activity that a bunch of different departments came together. And so the math department has a CSI set up, and it's being able to gather information based on blood spatters. So if you're interested in any kind of that criminology or criminal investigation, it's a really cool display. And that's going to be on Wednesday, the 6th, I believe. I'll try to remember to send out something and put it in the announcements in class so you have it. But if any of you guys go to it, and then today on campus and tomorrow, they're doing something called a STEAM blast. And so it's all the STEM majors and stuff. They're putting together some a scavenger hunt. And if you go to that, you can earn some extra credit. So there's a scavenger hunt and a form that you fill out, and you go to different sites, and each site has a different STEAM or STEM type activity that you can do. Okay, so those are 2 opportunities to earn some extra credit, and just to see how math is applied in a real life setting. The blood splatter one is pretty impressive. So, okay, so here we go. So we're going to start with just basic related rates. So here are your 3 questions, right? So you don't have to necessarily write things down, but just I want you to be aware of, okay, what am I looking for? What do I know? And what's the connection? You want to go through all 3 of those every time. So again, if you see the term, I'm going to do it in red. If you see the term rate or change, like an increase or a decrease, you will have a derivative. And with related rates, we're always going to do this based on time. We're going to find the derivative based on time. Okay? So this is why that one step that I said is redundant. You do it with every single term in your equation. Write this in front, because the variables have changed. Now it's no longer d dx. We're finding the derivative based on time now. Okay? So here we go. So just to kind of highlight what we're doing, the number 1, what's being asked. So this one's easy, right? We're finding dy dx. What do we know? Again, it's given to us. We know that dx dt is -2 and x is 2. Okay? And then the connection is just whatever the formula is, whatever given function or equation. Okay, so these are easy. These they just give you the information. It's when we get to the word problems that it gets a little more challenging. All right, so here we go. We're finding dy dt. That's our first question. We know that our change in x over time is -2, so it's decreasing. We also know that x is 2, and this is our function. So what we're going to do is we're going to find the derivative in terms of time of y, the derivative in terms of time of x cubed, and the derivative in terms of time of -3. Okay, now keeping in mind of what you're looking for, that is always super helpful because you know you have to have a dy dt in your function, right? So here we go. The derivative of y in terms of time is dy dt. The derivative of x cubed in terms of time, so our variables are different, so I'm going to use the power rule. And then dx dt, because again, I peeled that off, so what's left is dx dt. And then minus the derivative of a constant is just 0. Okay, so here's the good news. My dy dt is already by itself. I don't have to do anything with it. I have it already solved for it. All I have to do is put in my information. So x is 2 squared. My dx dt is -2, and it's because it's given to us. And so now I just have to calculate. So my y is changing. So 3 times 4 is 12 times -2. It's decreasing by 24. And this is that abstract. We don't know what y is. We don't know what exactly we're looking for. But we know that our y is decreasing by 24 based on whatever time it is. And the time can be different. The time can be in weeks, it can be in hours, it can be in days, it can be in years. So we're using all of those measures of time with one t, basically. Okay, so questions, comments? And you can see why the implicit differentiation is so important, because you can find the derivative of anything. Several years ago, I think one student said it was in 2012, there was a massive oil leak, and the oil spread just kept getting bigger and bigger and bigger, and it was spreading very, very quickly. Well, you can find how is that oil spread changing based on implicit differentiation. And one of the scenarios I saw, it was increasing by 125 cubic feet, right? So cubic means volume. So it was spreading out by 125 feet per, I think it was per minute. So it was just a huge oil leak. And it was, in the Gulf, it was underground. It was just spewing out of the pipe. There was a pipe that had broke. I think it was several miles down. So it took a while to get it fixed. So, okay, here we go. So what are we being asked? I'm going to color code it here. We're being asked to find dy dt. What do we know? And again, these are given to us, and you'll see on the next two, the word problems, where we have to find out what we know. Okay, so we know that when dx dt is -5, when x is 4. And then what's the connection? The connection is, here is that equation of a circle. That's our connection. Okay, so here we go. We're going to find d dt of x squared d dt of y squared and d dt of 41. Okay, so implicit differentiation. I have different variables. So the derivative of x squared is 2x. I peeled the 2 off. What's left is dx over dt. I have different variables again. So my derivative of y squared is 2y. I peeled that 2 off. What's left is dy dt. And then the derivative of a constant is just 0. Okay, now on both of these, I want you to notice something. Every time there's a different variable, I have a derivative, dy dt. I have a different variable here, dx dt. Same thing down here. I have different variables, dx dt, different variables, dy dt. So every single time you have different variables, you're going to have one of these derivatives. Okay, that's never going to go away. Because what you're doing is you're finding a derivative of x squared in terms of t. Well, you don't have a t here. So that gets taken care of here. The derivative of x in terms of t is right here. Here, I don't have a t. I only have a y squared. So this dy dt is taken care of. I'm finding the derivative of y in terms of t. Okay? So now I'm going to plug my values in. So x is 4. dx dt is negative 5. 2. Here's where there's a problem. But I'm also trying to find dy dt. So do you see how there are 2 different variables here? This is the one I'm trying to find. This one's a problem. Okay, so we have to go back to the beginning. So when you have 2 variables and one of them's y, you're going to go back to the beginning and plug this information in so that you can find y. So to find y, you're going to plug the x value into the original function. And then you're going to solve for y. Okay, so sometimes you got to do this. Sometimes you do, sometimes you don't. It just depends on how it's laid out. Okay, so I'm going to do that right here. I'm going to do it in a different color just so that it keeps it separate. Okay, so we have 4 squared plus y squared equals 41. So 4 squared is 16. So all I'm doing is just algebra, right? I'm just solving for a variable. So 41 minus 16 is 25. And now I'm going to square root both sides. So my y is going to be 5. Okay, now I can come back here and rewrite this. So 2 times 4 is 8 times negative 5 is negative 40 plus 2 times 5 and then dy dt equals 0. Okay, so once I find the y, now I can plug it in right here. And now I can finish because now I only have one variable. That's considered one variable that I can solve for. Okay, so I bring my negative 40 over as a positive 40. 2 times 5 is 10, so 10 dy dt equals 40, and then divide both sides by 10. So my dy dt is 4. So my y is changing in terms of time. It's increasing by 4. So with related rates, you'll always have an answer. That's the whole goal, is we're looking for how is our rate changing? Is it increasing or is it decreasing? And just sometimes you have to go back and solve for the other variable. And that's why I wait till the end. On the train one, the train versus car one, I knew I needed the C, so that's why I plugged it in first. So you could do that if you want. You can go ahead and solve for the other variable if you want. Just sometimes you're going to need it and sometimes you're not. So it just depends on how it's laid out. Okay. All right. Any questions on that one? Okay, so now let's get into some word problems. Okay, this is what you're going to see in the related rates. On Thursday, this is all we're going to do is just related rate word problems. So you're going to get lots and lots and lots of practice of just finding the information. What are you looking for? What do you know? What's the connection? Okay, so I'm going to write those 3 questions. So the first one is, what are we looking for? So here's your scenario. Cyborg Incorporated finds their revenue for the number of shirts they sell in advertising is given by, here's our function, R equals 90x minus x squared, okay? Where x is the number of shirts sold daily. This kind of information is going to be super important. X is the number of shirts sold daily. And R is the revenue generated, or the generated revenue in dollars. Okay, so it's not millions of dollars, it's not thousands of dollars, it's just dollars. And then X represents the number of shirts. Okay, the company also finds that the shirts are selling at a rate of 5 shirts per day. How fast is the revenue changing when 40 shirts are sold? Okay, so this is where going through those 3 questions are going to really, really help you. So the first question says, what are we finding? You are finding, put this in color, how fast the revenue is changing. So you are finding how fast the revenue is changing based on time. So again, when you see the word rate, or you read the word changing, increase or decrease, that's your derivative. So we are looking for how fast is the revenue changing. So their derivative in revenue in terms of time, that's what you're looking for. Okay, the second one is, what do we know? It's green. Forgot what color I used. Okay, what do we know? Well, we know that our shirts are selling, the shirts are selling at a rate of 5 per day. Okay, shirts are selling at a rate. So what does shirts represent? Shirts represents X. So our shirts are changing at 5 per day. So the number of shirts increases by 5 per day. So the derivative of X over T is 5. And then we have 40 shirts. So our X is 40. My dog's going to bark. I'm sorry. Katie. Okay. So any questions on how I got those 2 pieces of information? Do you see it? All right. And then the connection is my function. R equals 90x minus x squared. That's our connection. So there's our connection. Okay, so now you're off and running. You have everything you need. Now all you got to do is implicit differentiation. So we're going to try to do it in the same exact way. So we're going to find d dt of r, the derivative in terms of time of 90x, and the derivative in terms of time of x squared. Okay, now we're just going to do implicit differentiation. The derivative of the revenue, or how the revenue is changing over time. There's our dr dt, and look at there, it's exactly what we want. There is what we're looking for. So the derivative of 90x is 90. So I peeled the 90 off. What's left is my dx dt. The derivative of x squared in terms of time. So x squared derivative is 2x. And then I have dx dt. Okay, so once you find that implicit differentiation, now it's just a matter of plugging in the values that you figured out. You know dx dt is 5. You know x is 40. And dx dt is 5. And we are looking for how the revenue is changing. Okay, so 90 times 5 is 450. 2 times 40 is 80, times 5 is 400. So your revenue is changing by $50. Okay, so here is where doing the math is great. I think it's awesome. You did the math, yay. Now you need to interpret it. Okay, so here's your interpretation. Revenue is increasing by $50 when 40 shirts are sold at a rate of 5 shirts per day. Okay, so that's actually a good thing for the owner, right? My revenue is increasing by $50 when 40 shirts are sold at a rate of 5 shirts per day. Okay, now let's look at this even further, right? So that's the perfect way to do it. That's the answer to your question. That's how you're going to interpret it. But let me just change it up on you a little bit so that you can see how powerful this differentiation is. Let's say that our boss comes, right? The owner comes and he goes, man, 40 is not good. We're increasing our revenue by $50. I bet if I had more shirts, if I had 100 shirts, still selling them at 5 per day, I'm going to make bank. Okay, so let's try it. So we're looking to see how is our revenue changing. Again, the dx dt is 5. But now I have 100 shirts. Well, here's my 450. 200 times 5 is 1,000. 450 minus 1,000. Now I have negative, what is that, 550? So what happened? What does that, how would you interpret that? Anyone want to give it a shot? You guys are so quiet today.
You're losing money every time, like not just like selling them. Like every time you sell them, you lose money. You know, it's just like how much it costs you.
Okay, so but why? I have more shirts. Shouldn't I make more money?
They're being sold at a higher price.
Okay, they could be sold at a higher price, or maybe I'm not selling them, you know, for enough. If I have 100 shirts, that means higher costs, right? I have to get these shirts somehow, right? I'm not going to go out and steal them off of people. I have to actually buy the shirts. I have to actually put, labor into it. So I'm putting money out. There's a lot of other things that go along with just adding more product. And so a lot of times what happens, people in business, they think more is better. And it is not necessarily true. You will see that over and over and over again. A great example of that. Remember and I think they're still around, but it's not very many, the Krispy Kreme franchise. So when they first came out, everybody was just like, oh, Krispy Kreme is the best. It's so good. It's great. And so their marketing was fantastic. They got the word out. People were, clawing for these donuts, right? So they opened up franchise after franchise after franchise. Where I lived up in Northern California when they came out, we would go shopping in Reno, Nevada. We were about hour and a half from Reno, and that's where we would shop. And there was literally a Krispy Kreme franchise every other block. It was ridiculous. And so they opened up so many franchises that they put themselves out of business. Because one, the excitement died down, right? People were like, oh, they're not that great if you don't get them right out of the grease. And then they had way too much money in their marketing and in their setup costs. So they set up all these new franchises, but the income, the revenue was not keeping up. And so they closed down. So now it's almost impossible to find them. So they just don't have the numbers that they used to. So a lot of times what happens is a company has a great thing going, but they do too much too soon. And so they start losing money. So this is just this using implicit differentiation in a business setting. You can actually throw numbers in there and go, okay, well, what's the best thing that I can do? I was making $50 in revenue. My revenue was increasing by $50 when I had 40 shirts, but now my revenue is decreasing by $550 when I had 100 shirts. So I have to come back to, okay, where's a sweet spot, right? I want to make income. I want to make revenue, but I also want to have enough on hand to where I can be able to sell the product, whatever the product is. Okay, so it's that idea of there's got to be a sweet spot. All right, I don't know if I can do this. No, it won't let me. Never mind. Oh boy, what did I just do? Okay, all right. So, any other comments? Any other questions on that one? So let me type down here just so that we have it. So revenue is decreasing by $550 when 100 shirts are sold at a rate of 5 shirts per day. So on the test, this is how you guys are going to get your extra credit. You're going to show me the math. That's full credit, and then you'll get extra credit for being able to interpret your answer. Right? All right. This one, we have 3 things going. This will be our last one. We have 3 things going. We are going to find the rate of increase in cost. That's A. The rate of increase in revenue and the rate of increase in profit. Okay. So going back to what we are given, right? We are looking for 3 things. So we are looking for how the cost is changing based on time. That's A. B is we're looking for how the revenue is changing based on time. And C is how the profit is changing based on time. And there is a very close relationship between these 3 things. Okay, so if you remember, profit is found by subtracting the cost from the revenue minus cost. So let's do that first. So that we have everything set up, ready to go, and then we can do our implicit differentiation real quick. So our profit function is the revenue minus the cost. Okay, so now I'm just going to clean this up a little bit. So I'm going to put it in descending order. So negative 0.0001 x squared, 10x minus 2x is 8x, and then minus 5,000. Okay, so here is our connection. Okay, so the connections, we have 3 different connections. This is the connection for A, this is the connection for B, and this is our connection for C. So now we have all the information we need. Okay, what are we looking for? So those 3 questions again. We're looking for how the cost is changing, how the revenue is changing, and how the profit is changing. Okay. And then, what do we know? So that second question, what do we know? And we're going to use the same information for all 3 of these. Okay, so that information is not going to change on us. All right, here we go. Notice what the X represents. The X represents the number, the production output in 1 week, so that's our time, is X radios. So X represents the number of radios. Production is increasing at a rate of 500 radios per week. So there is our radios are changing per week. So our radios are changing per week and they're increasing by 500. Okay, so that rate term is going to be super important to you. I always forget what color I used. Rate of 500. And then the production is 2,000 radios. Okay, so our radios is going to be 2,000. And that's why you have to notice what the variables represent, because it's a giveaway to how to set these up. So our radios are changing per week by 500, and the number of radios is 2,000. Okay, so that's what we know. That's what we're finding, and we have the connection already. So let's do it one at a time. So our cost was 5,000 plus 2x. Okay, so here we go. We're just going to do them one at a time. The derivative of C in terms of time. The derivative of 5,000. 5,000 in terms of time. And then the derivative of 2x in terms of time. Okay, so here we go. Derivative of C in terms of time. There you go. There's your dc dt. That's what we're looking for. The derivative of 5,000 is just 0. The derivative of 2x in terms of time is 2 dx dt. Okay, because we peeled the 2 off and what's left is the dx dt. So our cost is 2 times dx dt, which was 500. So our cost is increasing by $1,000. Okay, so our interpretation is cost is increasing by $1,000 when radios are selling at a rate of 500 per week. Okay, there's your interpretation. Okay, and then B, we're looking for how the revenue is changing. So your revenue function is 10x minus 0.0001x squared. So you're going to walk through the process again. The derivative in terms of time, I'm going to write them all so I don't have to keep changing my colors. We have the revenue, 10x minus 0.0001x squared. I have the right number of zeros, right? 3 of them? Yep, okay. Okay, so here we go. Implicit differentiation using the same things that the same information. The rate is changing at 500 and we have 2000 radios. So we have dr dt, that's what we were looking for. The derivative of 10x in terms of time is 10, and what's left is dx dt. The derivative of 0.0001x squared is 0.0002x. So I peeled that off and I have dx dt still. Okay, once I have the implicit, now I can just plug in my values and calculate. So our radios we're selling at 500 per week. The number of radios we have is 2,000, selling at 500 per week. Okay, so our revenue is changing. So this is 5,000 minus, I think it's 200. Yeah, so 5,000 minus 200 is 4,800. Okay, so our revenue is doing good. Even though our costs are going up, our revenue is okay. We're still increasing our revenue. Okay, so the interpretation would be the revenue is increasing by 4,800 when there are 2,000 radios being sold at a rate of 500 per week. Okay, so again, that's that idea that it's that instantaneous rate of change, right? We have information at a very specific point. And that's what makes calculus so great. Algebra is just kind of, it gives us, one thing at a time, where we can now use this exact same derivative and change the numbers, and we can see how our revenue is going to change. Okay. And then the last one, so guess, what do you think your profit is going to be doing? If revenue is increasing by 4,800 and costs are increasing by 1,000, what do you think profit's going to do? Any guesses?
You said costs?
Profit. What do you think the profit will do? We know the costs, we know the revenue. What do you think profit's going to do?
3,000.
Go up.
Okay. So Orlin, you had it. So it's going to go up. So George, you had part of it. It is going to go up. So remember that scenario that profit is your revenue minus your costs, right? If the revenue is 4,800 and the costs are 1,000, the profit should go up by 3,800. Okay, so let's try it. We know what our profit function is. So this is C. So our profit is a negative 0.0001x squared plus 8x minus 5,000. Okay, so we're going to do the exact same thing, exact same scenario, same information. We're going to find our derivative in terms of time, derivative in terms of time, derivative in terms of time, derivative in terms of time. Okay, so we're good there. So here we go. The derivative of p in terms of time is dp dt. The derivative of negative 0.0002x dx dt. Derivative of 8x, so plus 8 dx dt. And that just goes to 0. Derivative of 5,000 just goes to 0. Okay, so now I'm going to put my values in. X was 2,000. Dx dt was 500 plus 8 times 500. So we have a negative 200 here when I multiply all that out, plus 4,000. And there it is. Our profit is changing and increasing by 3,800, which makes complete sense because if profit is revenue minus cost, if my revenue is changing by 4,800 and my costs are changing by 1,000, that makes complete sense. Okay. So the interpretation is the profit is increasing by $3,800 when 2,000 radios are sold at a rate of 500 per week. Okay, so when you interpret these, you have to be very specific. You have to say how many items you have and how fast the items are changing. Okay. All right, we made it. So on Thursday, I'm gonna do very little talking, and we're gonna work in breakout rooms on different word problems, and then each breakout room is going to come back to the main room, and we're gonna each breakout room is going to talk through their particular problem, and then give an interpretation. Okay. All right, guys. If you have no questions, we're good to go.
Miss, I just wanted to ask you if the review was already up for the second exam.
Yes. So let me look in our class. I believe it's in the modules. Let's go to modules. So go into module 2. It's module 2. Yeah, module 2. And at the bottom, it says test number 2, review and solutions.
Okay,
So
got it.
here's the review and there's the solutions. And here's another review that I'll probably use on next Tuesday because your test is on Thursday.
Okay, perfect.
Okay.
Thank you, Miss.
You're welcome.
Bye. Have a good one.
All right, you too.